Good afternoon, everybody. I'm Gillian from Nokia. This is not my first LINX event, so I know quite a few of you already. However, this is the first time that I've actually done a public presentation. So just managing your expectations, I shall do my best, and I'll try to speak nice and slowly, because where I come from, the tendency is to speak at 100 miles per hour. So, following on from my colleague Jeff was saying, what we were talking about, the demands on power that our data centers are having, I thought we'd have a few moments to talk about optics and how we can actually, their future evolution can help to manage this power crisis, and if there's anything that we can do to make them more power efficient. So optics are now everywhere. Initially, these were delivered in optical line systems to replace copper for long reach and subsea applications. They exceeded the bandwidth at further distances than traditional copper could do. This optic functionality was then embedded into a compact transceiver, which could be plugged directly into the router. So as well as offering simplicity, we had some power reductions and massive space reductions there as well. On top of this, we had better visibility of monitoring with capabilities than we would have had before. With the change in the traffic, we had edge compute, we had then later AI. These demands for bandwidth then extended to be inside the data center, so we had to look at some solutions here. So from traditional data centers to AI clusters as well, to the point now where actually in the data center optics account for 50% of power usage. So what's changed in the data center? What's with all this new bandwidth that's needed? So traditionally, I guess we had mostly north-south traffic. We made web requests, we did files, the traffic came into the data center, went to a server, to the compute, and out again. As we had cloud compute, we then started to see more computer to computer or GPU to GPU connectivity, leading to east-west traffic. So traffic no longer just exited and entered the data center, but it went across the data center. So a lot of the traffic now stays within the data center. So this has posed a problem. So we now have the need for, with AI, not only do we have a need for, the traffic patterns are different. These are large, long-lived flows where they're very, very touchy and very prone to any errors. They don't cope well. So we need to offer greater bandwidth to sort of to improve the reliability. So we need higher bandwidth in the data center. And of course, with AI, we now need, there's no longer enough computing in one rack. So the compute and the GPUs must spread out of the rack, across the row, across the data center. So as well as needing the bandwidth, we now also need distance. And as we probably know, bandwidth and distance do not go hand in hand, which leaves us with a problem. All of a sudden, compute, which could stay inside your data center, the data center then reaches its power or maybe the space limits, so you can no longer fit any more racks of GPUs in there. We have to move out of the data center, perhaps to a new site across the campus. At the moment, with traditional PAM4 modulation, which we have now, these campus distances can be met quite happily with our standard optics. For example, we've got their ER that can get to approximately 40 kilometers, maybe a little bit less, but that's good for many of our applications. That's at 400 gig. Now we're at 800 gig today. So 800 gig, now you can see the distance is reducing. So no longer can our ER optics cope with these distances. So we may say, well, let's go with ZR. ZR, that's all very well. Yes, we can get distances of maybe 100 kilometers or more with ZR+. However, these are power hungry. It's complete overkill. They are more expensive to buy, more expensive to run. So that leaves a little bit of a gap here. How are we going to meet the need of the sort of, say, campus data center? So if you look in the pink area here on the graph, this is our problem area, and we feel this is going to be met by coherent light. So we're using the same modulation as you'll see within your ZR optic, but this is optimized for power for the shorter distances. So this is it's a much better solution, and you can see here that sits right nicely in the zone here between 10 and 80 kilometers. Okay, we think, all right, we've got at least an improvement here, an optimization, lower power to deal with our data centers. And now, of course, you've got the gigafactories. So this is no longer big enough now. Perhaps you've exhausted the power in a particular region. Let's spread out. We're now going to go longer and longer distances. So this is where we've got ZR. And at the moment, we've got ZR plus at 800. 800 gig is where we're at. And this is what it looks like. Have any of you ever actually managed to hack your way into a transponder just to see how it looks on the inside? No tinkerers? Okay, well, anyway, this is it, as exciting as it is. Two major components here. We've got the DSP, which is basically the brains of the transponder. This is doing the serialization and deserialization of the electrical signal, serializing it ready to be transmitted onto the optical line. And then you've got your T-rotor there. That's your transmit, receive, optical subassembly. And that's basically just, as it says, transmitting and receiving light across the line. So this is what we've got today, 800 gig. The same modulation, the same technology will see us through to the next generation of 1.6 tera. We just obviously need to do a bit more work on our signal processing there, a bit of beefing up. But basically, the technology, this will see us through. So this is for longer reach, but what about inside the data center? I mentioned earlier that now our optics are accounting for 50% of the power usage in the data center, so surely we need to do something about this. So we talked about the GPUs now spreading out beyond the rack, across the row, across the room. So what are we going to do to deliver these distances? Yes, copper's still used. We've got DAC cables, still probably the preferred choice for the lower power consumption, but this is only good really for up to 5 meters. For the sort of that gap in the market between 5 and 500, we need to do some power optimization. So one of the big ways of doing this is we can look at redesigning the packaging altogether. So by removing the DSP, your signal processor, from the coherent optic and passing that functionality onto the DSP already embedded in your router, this can actually you can actually get a power reduction of maybe over 50%, up to 50%, should I say. And then we can take this one step further with, it's not on here, I'm afraid, but we've got co-packaged optics. And what that does, it doesn't just take your signal processor, but it takes your optical subassembly as well. And it builds this all into the router. So all you've got now on your faceplate are some connectors to plug your optics in. This is even further power savings, taken to approximately about 1/3 of what you would get with your linear optic. Disadvantage of this, though, and it's quite a big one, is you can imagine if you've got all your optical functionality inside your box, if you then lose one laser, one port goes down, then it's going to be a nightmare. You're going to have to rip out your whole router, which is that's quite a big thing, really. So we made that decision. Is it worth it for the cheaper power? Well, perhaps we'll have no choice one day, but this is how we're looking at the moment. So just a quick summary. So yes, optics are now everywhere. They're no longer just a little pluggable that you stick in your router and have to worry about whether or not it's longer, the reach of the optic longer, or the speed. With bandwidth doubling every 2 years, we expect that by end of 2027, that we'll be at 1.6 tera. We believe we have the technology to deliver this with ZR+. And then for our multi-site AI clusters, with the compute expanding out of the data center, how we think coherent light is the technology that can bridge that gap between ZR+ and your traditional ER, for example, PAM4 optics. By redesigning the packaging of your optic, we feel that this can address the up to 70% power saving in the data center. This is significant. So yes, in summary, I think optics are actually a big thing, and I think they do actually have a part to play, and they could be part of our future solution. And that's all from me. Any questions? I'll be around for another half an hour or so, so please come and find me at the Nokia book and pick up a yo-yo while you're there, because you've got tons to carry home.